In today's video, we're going to finally talk about stack cookies, something that we've been sort of looking at and discussing all semester, but we haven't taken the time to really sit down and define what they are. So we're going to finally do that today. What is a stack cookie and what is the importance behind it? Well, where they really come into play and why I've been able to kind of push them off here for the last few weeks is that we'll really start talking about them when we move into more of the exploitation phase of the course, when we're going to do some buffer overflows and we're going to talk about exploitations and some of the mitigations that are put into our programs to prevent things like a buffer overflow. What the stack cookie helps to do is, one of the biggest things is to prevent buffer overflow or to detect a potential buffer overflow attack. So when we talk about a buffer overflow, what we're talking about is in a program, trying to copy a larger amount of data into a smaller data source. So let's say that we have two buffers, and you can just think of buffers like an array. Right? Let's say that I have two char arrays and I want to copy input from a user into a different buffer, a different char array. So if I allow them to just input whatever they want, I don't constrain the amount of input, what if they input 20 bytes of data and I'm trying to copy that into a 10-byte buffer, right? There exists the potential for an overflow. And what will happen when we talk about, and this is stack-based, but what can happen then is that we start to overwrite contents on the stack, memory on the stack, and that can lead to exploitation. That can lead to the correct type of input overflowing that memory and allowing that attacker to take control of the execution of the program. What you'll see is one of the primary mitigations for that is the stack cookie. It's also called a canary. It's also called a stack guard. So it kind of depends on the context. Generally, they're all talking about the same thing. And what these values can be used for is that they can be put on the stack for when a function is executed, where a function uses a buffer, and that value then, that cookie can be checked when the function is done. If that cookie has been modified or changed, then the assumption is made that an overflow was attempted or occurred, and the program is just terminated. There's a fault in the program, and it just stops running. Okay, so big picture, how do they work? Well, we have our stack, and this is how we've been using, or I've been drawing the stack diagrams, such as this. Right? Here's essentially the base of our stack, the highest addresses. Stack grows from higher, which is these addresses right here, to lower, which is 0, which is right here. All right, so we can see that. When we have our stack being set up, our stack frame being set up, right, we have the return address from the call, which is right here, and then depending on the compiler, you can see that this canary is inserted, possibly here, possibly here. The idea is, or the important thing about this, is that this canary or this cookie is inserted before any buffers are used. Okay, so let's say that this is a buffer, right? Local string buffer, so a stack-based buffer. You're given an address for this buffer, and these are 4 bytes wide, right? Because remember, memory on our stack, a 32-bit system, are 4 bytes wide. So each one of these blocks can represent 1 byte. So we get an address for a buffer. That address is going to point to this to this location on the stack. When we start writing contents into that stack location, we're going to write in this direction, and then it's going to wrap, and it's going to write in this direction. So depending on the size of our buffer, we're writing essentially down the stack. We're writing from a higher address to a lower address. So if a buffer overflow occurs, what can happen? Well, if we continue to write, then we can overwrite EBP, we can overwrite the stack cookie, and this is where our problems come in. If we can overwrite that return address, then we can take over the flow, the execution of that program. And so what the cookie hopes to prevent is that when that value is checked, the return address has not been allowed to be overwritten. If it has been overwritten, the cookie has been modified and the program can terminate. It can detect an attempted exploitation, and it can stop that from happening. It can stop the attacker from overwriting that return address. Okay, one thing to keep in mind is that the compilers will do it different. We've been predominantly focusing on Microsoft using Visual Studio. GCC and Clang and some of these there's a lot of different compilers, and each one kind of approaches it a little bit differently. Since we're using Microsoft, we'll focus on Microsoft, and what you have to understand is that not every function is going to have a stack cookie. The stack cookie will come when that compiler determines that it should be applied. So what Microsoft will do, and you can read this little blurb right here, Microsoft will say, okay, this is how we determine a string buffer, and that this is the conditions in which we will add a stack cookie to a function. Okay, so the compiler will modify that function in order to include this cookie, but not every function will have it. Okay, the cookie, it's a static value. It's going to be determined at runtime. So once the program is ran, the operating system will generate this cookie value at runtime. So it's going to be unique every single time. If it wasn't, then as an attacker, we might have the ability to figure out what that cookie is and use that in our attack. So it's going to be configured dynamically at runtime. It's a D word, so it's 4 bytes, and it's stored in the data section when the modules are loaded. How does the XOR work? Or I mean, how does the security cookie get set? Well, these are those instructions, the ones that we've been predominantly ignoring from the beginning of the semester. This is it. So we move that security cookie, which is defined at runtime, right? That's just a segment in data, the data section where it's now stored. So it moves that value into EAX. EAX is XORed with EBP, and then that value, EAX, is stored into var_c. So this we can now define and rename an IDA in our database as the cookie or the guard or the canary or whatever you want to call it. Okay, so as part of our prologue now, functions that have a buffer used within them, this is kind of part of our prologue, and that we'll have push EBP, move ESP EBP, and then we'll have the setup for the stack cookie. Okay, what happens when the function returns? This is the important part, because this is where it's going to be able to determine if an overflow occurred. And this will check whether it was malicious or not, because right, the program doesn't understand the intent behind the overflow. Overflows can occur even if the intent was not malicious. So what will happen? Well, the cookie is compared. So we move the cookie, so var_c, remember we determined previous that that is our cookie. That's moved back into ECX. ECX is XORed with EBP. Right? And remember that when you XOR a value against another value and then XOR it again, you should return the same value. So in the previous instruction, we moved the security cookie into EAX, we XORed that with EBP. Okay, so now if we move that into ECX and XOR that with EBP, we should get back the same result. So that's XORed, the result is stored in ECX, and then there's this call to security check cookie. Now, your version of IDA might not do a great job of identifying this function name right here. So what will help you is that you identify that cookie value, you rename it. Okay, and usually in this prologue, it's a little bit clearer what's going on here. So you rename it, and then when you see these instructions and this call to this function, that way you can identify that as the security cookie check. Okay, if we followed that function, security check cookie, you'd see this is what it does. It compares that original cookie value, underscore underscore security cookie, okay, which is originally where it came from, right here. Compare that with the value that we just got in ECX that we essentially passed to this function. Okay, so we'll talk about calling conventions this week, but this value is being moved into this register ECX, and that's how that function is calling it. So not every function expects arguments to be pushed on via the stack. Okay, if we do the comparison, if it's not 0, it jumps to this location. The program will crash, it will terminate. Otherwise, it just returns. Here's another example. So you can see we have some different arguments right here. We'll talk about those, I think, this week or next, as far as some of the arguments to our program, arguments to main. And then we have these locals. And so we can see var4, var18, var1c. And just based off of the distance between these two variables, we can assume that that's an array, that that's some sort of a buffer being used, because there's a large distance. This variable here, or that offset, and there's quite a bit of space there on the stack. And then this is going to be our stack cookie, so var4. Okay, furthermore, we can look at those instructions and we can see we move security cookie into EAX, XOR EAX with EBP, and then move EAX into var4. So these instructions right here are our cookie. So this value right here is our cookie. Okay, there's the check. So var4 is cookie, move it into ECX, XOR that with EBP, call security cookie check. If we jump there, you'll see just like you saw in the previous. We compare ECX with that original value, that static cookie value that was figured at runtime, and then it jumps, if not 0, because of the comparison, to this failure where it reports a failure and the program crashes. Otherwise, it just returns and it executes or returns normally. Okay, so with this diagram here, I just wanted to focus a little bit more on how that value, that cookie, can get overwritten. Okay, you'll notice between this diagram and the first is where that cookie is being placed on the stack. You'll see here that I have the cookie being after EBP. In that first diagram, the cookie was above EBP. The important thing is that it comes before this return address. Because right here, when this program gets ready to return, this is what we're going to pop off the stack and set into EIP. If we can take control of this as an attacker, then that means we can control the execution of the program, or we at least potentially can. So here you can see var4, var18, var1c. Okay, var18 is our buffer, and here we have EBP minus 18 as our buffer. When we start writing contents to that buffer, we have from minus 18 hex to minus 4, so we could figure that out real quick if we wanted to open up a calculator. So we'll just take 18 minus 4, which of course is 14 hex, which if we convert, we have 20 bytes. So it's a 20 byte buffer. So we have 20 bytes between the start of this buffer until it should end. If we write more into that buffer, even 1 byte, then that's going to change this cookie value, because we're writing in this direction. We're writing from that lower address to that higher address, right? The cookie is at offset minus 4. This is EBP minus 4. This is EBP minus 18. So if we overflow this buffer, even by a single byte, by a single bit, then that'll change the value of cookie. So that when we do that check, when you see that check at the very end, if we have somehow overwritten the value of var4, that cookie, that's XORed with ECX and EBP. So that cookie changed, we XOR that with EBP. If that's not the same, this comparison is going to fail. One bit difference and it'll fail. Okay, so even if we happen to manage to overwrite the entire thing and EBP to the return address, we check the cookie before the function returns. If that value is not the same, it doesn't return, right? It crashes. So that's what this diagram is trying to show us, is that that buffer is allocated here. We overwrite from a lower to a higher address. We write down the stack, and if we overflow the buffer, we're gonna overwrite that cookie value. If these were swapped, same thing. We'd overwrite EBP, we'd overwrite the cookie value, and that check at the end would still detect that, causing the program to terminate. Something else that you'll notice here as you work with functions, compilers that implement the stack guard, especially with Microsoft, is that you might notice variable reordering. And this is just an example of, we have this sample program main, we have a bunch of locals, ix, y, z, and zz. And you can see they're all initialized with a value, 0, 1, 2, 3, 4. So it's very easy to identify what these are. This is the resulting disassembly of that. And what we can see, just based off of how that data is moved into those locations, we can identify which variables are which. So we can see var4 has 0, that is I. So this is I, this is x, this is y, this is z, and this is zz. As these local variables are declared, they're allocated space on the stack. So this would be, when all of the space is allocated for these variables, this would be the closest to the top of the stack, right here, right? And I could draw that out. So minus 14, that's zz. Then we'd have z. Then we'd have y. Then x. Then I. Right? ESP would be pointing right here. So that'd be the top of our stack. Okay, of course we have EBP, old EBP, and then our return address. Okay, so that'd be our stack layout. Let's say in this function, though, we modify it and we add a buffer. You can see right here, int I, x, y, z, and then instead of zz, I have buffer a. A is an integer buffer. It's 5 elements. Each element is 4 bytes, so we have a 20 byte array. Okay, what would happen? Well, here we might think that instead of this being zz, what we'd have is we'd have what did I call that? A? Yeah, array A. So let's just get rid of zz. Let's say that this is now A. And of course our stack would point here, and this would just be 20 bytes. And then we'd have Z, and then Y, and then X, and then I. But what actually will happen is some will do variable reordering. And what you can see now is that we have var minus 4, var minus 18, 1C, 20, 24, 28. We can identify some of those based off of the values that were moved in. So 0, 1, 2, 3, so 24, 20, 1C, 28, that would be I, X, Y, Z. And then var 24, oh, that's the same thing, that's I again. Sorry about that, you can see that we're using a loop right here. Because we don't use right now in this code, we're not using A yet. A is used inside of this loop. Okay, so you can see that right there. So that's just I, var 24 is I. Okay, but what you'll notice here is that even though int A was declared last, when it reordered the variables, it got moved kind of to a different location. Var 18, this is our array right here. Part of how we can determine that is based off the size. We did that calculation previously, 18 minus 4, 14 hex. 14 hex is 20, so 20 bytes. But you'll notice that it's not the same. It's not down here at a higher, a higher value, higher offset. It's right here. It got reordered. It's a different place on the stack. So if we drew the stack out, what we would have is we'd have our cookie, which is var underscore 4, and then we'd have our array. I'll just call that A, which is var underscore 18, and then we'd have the rest of our variables. Right? So 0 is into var 24. Var 24, that's I. 1C is 2. 2 is Y. 1C is actually the next. It gets a little bit more confusing, but we can continue on and we can figure out the order if we needed to. The important thing is not so much that we can recreate that. The important thing is to understand is that it might get reordered, because what we want to have happen is if A is overrun, if it's used as a buffer to be overran, one bit gets overran, we want it to overwrite the cookie right here so that we can test that. If we didn't do that, if that didn't get reordered so that the next thing that comes after that buffer is the stack cookie or the guard, then what would happen is that, let's say that we have this original example here, and let's say that this is, our cookie is, it's somewhere lower on the stack. So let's just put it right there. Well, now if our array is here, we've got all these other variables, all these other locals that we could overwrite. If we can overwrite I or X or Y or Z, then we can still overwrite those. We can still change their values. And while we may not be able to overwrite this return address, we can still potentially change the execution or the flow of the program. And the problem would be is that if we can overwrite those and not overwrite the cookie, we can still abuse the program. And so that's why you'll have that variable reordering. And it can kind of change up everything like you're seeing here. It kind of changes up the location of these variables on the stack, but the most important part is that it moves this array, this buffer, so that if it is overflown, it overwrites the cookie. That way when it returns, it checks that value. If the value has been modified, it can crash the program and not allow that attacker to continue to exploit it. Okay, as I talked about, there are other compilers that you can turn on. So when you compile your program, oftentimes you can enable or disable. Most modern compilers have this protector on by default. So if you look at GCC, you'd have to look at the FStack protector, FStack protector all, and then there are some additional references here. So that's all I have on the stack cookie. Hopefully this generally makes sense as far as how that cookie is used. Again, when we talk about buffer overflows and do more dynamic analysis, we'll revisit this concept of the cookie, and you'll see it actually helping and preventing an overflow. So we will revisit this topic, but it's not entirely clear. Hopefully the objective for this video is that you have a general understanding of how this works, of how essentially this diagram right here, that this cookie is put in, it's created by the compiler to help detect that overflow. And those are what you're looking at. So when we see these this in disassembly in IDA, we can identify these instructions as setting up the stack cookie for that function, checking it to determine if that was modified. All right, that's all for the stack guard. Let me know if you have any questions on that. Otherwise, I'll talk to you in the next video. Thanks.